Hi, this is Mike Pruner. I'm doing a technology critique on Desmos again. I know we've seen a lot of Desmos. The activity that I'm going to be using Desmos for today has to do with regressions, which you can see in the Foundations of Math 12 course. You see just a quick glance at the IRPs here that you use regressions for polynomial functions, exponential and logarithmic, and also for sinusoidal. I do have a worksheet all set up here that I am not actually going to go through in great detail because I don't have a whole bunch of time for that, but I will leave this worksheet also in the folder so you can take a closer look at it if you're interested. I love regression analysis in the Foundations of Math 12 course because I find it's really something that students can grab onto as a real application of mathematics. Almost everybody can appreciate in a time where they can, whether they're in a psychology course or a biology course or a statistics course, where they're going to be collecting data and trying to come up with an equation that represents that data or that relationship. So it's a really nice topic to go through with the kids. They usually grab onto it quite nicely and they enjoy it. What I thought I'd do for this critique is I really wanted to compare Desmos with the old traditional graphing calculator, just so you can really see the differences in the technology. So I'm just going to go through the first task here real quick here with the graphing calculator. I'll pull it up. You can see how clumsy this calculator really is. If you've ever done this before, you're probably familiar with the steps. The first thing to do is you have to go into the L1 and L2 list and enter that data, and then you have to set up your window, which if you're not comfortable with the calculator can be half a class in itself for setting up a window. Then you have to go and turn your stat plot on, which I've already done, and you have to go to your y equals to make sure there's no functions in there that are going to throw off your sketch. Then you can go hit graph and you can see that the plot, it does look somewhat linear. And at this point here, you'd have to make a decision as to what kind of graph you think, or what kind of relationship goes through those points. Once you've made up your decision and you say, hey, I think it's linear, you now go to stat, over to calc, down to linear because I think it's linear, and you press enter and enter on all of these things and calculate, and there's my linear regression. It's just kind of like a black box. You have no idea where these numbers are coming from. This is where Desmos, I think, really shines. You'll see in a moment. Another poor thing about the traditional method is now when you go to the graph, it's like, bam, and it's like, can't really see that line anymore. I sure wish I could see the line go through the points. And if you get out and how the regressions go on, it's like, oh, for crying out loud. So what you can do with the calculator, and unfortunately this is quite tedious, is you'd have to go to the y equals menu, select vars, we want a statistic variable, so enter on that, over to equation, enter a regression equation, and that's how you get the regression equation into the y equals. Hit graph, and this is your wonderful moment in the class. Unfortunately, only 2 students are able to get through to this step because everybody else is still probably setting up their window. So the old technology method, not only was it a black box, but it was also very difficult to follow all the steps properly and get to your actual I'm just hitting trace, and I'm just remembering how students would trace on points and not trace on the line. Like, it really is not a friendly technology to use for a classroom. So here I am now, I'm tracing on my relation. So let's compare this now to Desmos. What I'm going to do is I'm going to put the exact same points into Desmos, and we'll see how quick I can do this. So let's open up my Desmos. So here's my Desmos application that I made. You can see I've got different folders going down the left-hand side here. I've got one folder for entering my data, and then I've got my last folder for changing my parameters, and then all the other folders are the different regressions that you might want to use. So let's just quickly go put this data in here. I'm going to put the y in first because I have it in my memory. So 0, 3, 5, and 10, and I believe the x's were 0, 1, 2, 3, oops. 2 and 3. So here I've got the data in here, and we can see as I'm pinching and zooming with my fingers on the screen here, I can see that it does look linear, and it was so easy to put into the application. It does look linear, but it also, I mean, if you really are wanting to match the points, I could almost imagine maybe a cubic going through these points. So when I'm filling out this worksheet here and I write, well, I think it's linear. Why do I think it's linear? I get to spend some time writing that in this box. Or I think it's cubic. Why do I think it's cubic? And I can put that in here. Let's go back to the Desmos here. I do think it's linear, so let's start off with the linear regression. I'm going to go down to the linear regression folder, highlight the graph for the linear regression, and now I go down to the parameters and I get to actually try and fit this line to those points. So as I move the A, I can see that's definitely affecting the slope, so I'll try and get the slope about right. And then move the B. I can get the B down to right around here, and it's like, yeah, I think that's a pretty good regression. You know, it's a line of best fit. It looks like it's not going through all the points, but it's definitely close to all the points. So I'm going to be happy with that, and I'm going to write y equals 3.5x minus 1, and I'm going to write that right in here. That's my regression equation. If you follow the steps in the worksheet, the next step is to go and chat with a partner. Compare your regression equation with that of another group. And I can guarantee you that they're not going to get the same equation. So this is a nice time for discussion. What is similar in their parameters, what is different in their parameters, who is more accurate? That's step number 6. How can you compare the accuracy of your regression with that of another? And that's where this last column comes in, error. And I've left this very open because I think it'll be really neat to see what students come up with for deciding on, how do I judge the accuracy of this? Desmos is set up quite nicely to look at points and compare points. 2,6 compared to 2,5, I'm only one off here. How am I on this one? I'm only 0.5 off on this one. So that might be one way that students come up with for comparing accuracy. Another way might be, how many points did I make it through compared to you, or compared to another group. So I love that this is just so open for students to discuss and to come up with their own way of describing error and accuracy of their regression. The very last step in the exercise asks students to enter a third column. And now this is definitely untraditional. I don't think many classes would be entering this third column into Desmos, but let's just do that right now to see what happens. So z equals f of x minus y. I'll put that right in here. And what this does, as you can see, is it now creates a new set of points. If you look at what this is actually doing, it's actually comparing my function value with my actual table value. So these new points are actually graphing my error. Okay, and in the worksheet, it never actually talks about that. It really leaves it open. Go through that step of creating the third column, and what do you notice about the table? What do you notice about the graph? What do the new points in the graph represent? How can these new points help you find the best regression? You can see here now as I'm adjusting my parameters that these new points are now, you can say, well, if these new green points are my error, then I really want to get my error as close to 0 as possible. And maybe this is a nice visual way of trying to create the least amount of error. Further to that, we can actually go and look at that table and say, well, if this is my error for every point, maybe one way of deciding on accuracy might be to maybe average these errors, possibly. I also wanted just to show you, what if a student didn't think this was a linear graph? What if a student looked at this graph and thought, I think it's cubic. Okay, and this activity is open enough that you can actually go through that. Now, I've actually already done this, so I'm not going to waste your time with it. So if I go in here, I'll open up my, I think it's under 1B, where I've gone through an example of, see, there we go. So this is, again, this exact same set of data, but now we can see that a cubic actually fits it quite nicely. You can see the parameters I chose for the cubic here. seems to go through the points. If you look at that error now, the error are my green points. You can see that they're quite close to the x-axis. So I really like this activity for regressions because it's no longer a black box. It's not some magic computer that's generating a regression formula. It's a very hands-on experimental approach for coming up with a curve of best fit that has real application. And it also introduces, even though it's not in the IRPs, it introduces a very valuable discussion about error and accuracy, and it leaves it open enough that students are able to kind of create their own definitions about error and accuracy with respect to these regressions. So I think it's a neat activity. I'm looking forward to doing it next year if I'm teaching Foundations of Math 12, or I'm looking forward to hearing some feedback with anybody that's given it a try. So thank you for your time. Goodbye.